Let us travel back in time, not just thousands of years, but millions. We arrive in a world that is both strange and familiar. This is the Permian period, about 252 million years ago. The Earth has one giant continent, we call it Pangaea. Stretches from pole to pole, a vast supercontinent surrounded by a single immense ocean. The climate is warmer and drier than today. Great deserts cover much of the interior of this massive landmass, but there are also vast forests, not of flowering trees, but of giant ferns, conifers, and other ancient plants. This world is teeming with life, a complex and beautiful tapestry woven over millennia. Look closely at the land. You will not see birds or mammals as we know them. Instead, strange creatures roam. Reptile-like animals are everywhere. Some are large and slow, like the Scutosaurus, a heavily armored plant eater. Others are fearsome predators. The Gorgonopsians are among the most impressive. They are the size of a bear, with long, saber-like canine teeth. These are not dinosaurs. They are synapsids, the distant relatives of mammals. They are the dominant land animals of their time. They live in a world of constant struggle and survival, a vibrant and dynamic ecosystem that has been stable for a very long time. Now let us dive into the warm, shallow seas. The oceans of the Permian are just as full of life. Huge reefs stretch for many miles, but these reefs are not made of the corals we see today. They are built by different creatures, sponges, algae, and bryozoans. They create complex homes for countless other animals. Fish of all shapes and sizes swim through these underwater cities. Some have heavy bony armor, others are sleek hunters, ancestors of modern sharks. The water is clear and sunlight filters down, illuminating a world of incredible diversity and wonder. It is a world in perfect balance. Among the most common creatures crawling on the seafloor are the Trilobites. They have been on Earth for over 250 million years. They are true survivors, having weathered past extinctions. They scuttle along the seabed, some small, some large, with their distinctive three-lobed bodies. Alongside them are sea scorpions, ammonites with coiled shells, and brachiopods, which look like clams but are a different group entirely. The Permian world, on both land and sea, is a testament to life's incredible power to create and to thrive. But this long age of stability is about to come to a terrible and sudden end. Deep beneath the surface of Pangaea, a destructive force was stirring. In a remote part of the supercontinent, in what we now call Siberia, something catastrophic was beginning. A huge plume of molten rock, or magma, was rising from deep within the Earth's mantle. This plume was gigantic, far larger than anything humanity has ever witnessed. It pushed upwards against the Earth's crust with immense pressure. The ground would have trembled for years, a warning of the unbelievable power that was about to be unleashed upon the world. The animals living there could not have known what was coming. Finally, the crust gave way. The ground split open, not in a single volcano, but in a series of enormous fissures. These cracks in the earth stretched for hundreds, even thousands of miles. From them, lava began to pour out. This was not a short explosive eruption. It was a relentless flood of molten rock that went on for an incredibly long time, possibly up to 1 million years. Wave after wave of lava spread across the land. It covered a vast area, burying everything in its path under a thick black blanket of basalt rock. This was the birth of the Siberian traps. The scale of this event is difficult to comprehend. The eruptions released an enormous volume of lava. Scientists estimate it was enough to cover an area the size of Europe, several kilometers deep. The Siberian traps are one of the largest known volcanic events in Earth's history. The lava flows themselves were destructive, wiping out all life in their immediate path, but their direct impact was small compared to what they did to the entire planet. The real killer was not the lava on the ground, but the vast quantities of gases that were released into the sky. These volcanic fissures acted like giant chimneys. They pumped colossal amounts of gas and ash directly into the atmosphere. The sky would have turned dark, filled with sulfur and other toxic compounds. The sun would have been dimmed, and a strange twilight would have fallen over the world. The gases included carbon dioxide, methane, and sulfur dioxide. Each of these had a powerful and deadly effect on the global climate system. The Siberian traps had pulled a trigger, starting a chain reaction that would soon engulf the entire planet and push life to the very edge of annihilation. The gases pouring from the Siberian traps began to change the world's climate almost immediately. At first, the sulfur dioxide and ash had a cooling effect. These particles reflected sunlight back into space, causing a brief volcanic winter. Temperatures on Pangaea may have dropped for a few years. This sudden cold spell would have put immense stress on the plants and animals that were used to the warm Permian climate. Forests would have struggled and animals would have found it harder to find food. But this initial cooling was just a prelude to a much greater disaster. The worst was yet to come. The real problem was the carbon dioxide. Unlike the ash, which fell out of the sky relatively quickly, the carbon dioxide stayed in the atmosphere for a very long time. It is a greenhouse gas. This means it traps heat from the sun, preventing it from escaping back into space. As the Siberian traps continued to erupt for thousands of years, the amount of carbon dioxide in the atmosphere soared to extreme levels. The short volcanic winter ended, and the planet began to heat up. And it heated up very, very quickly. Global temperatures rose by as much as 10 degrees Celsius. This rapid global warming had devastating consequences. The great deserts in the center of Pangaea expanded, making vast areas of land uninhabitable. The lush forests that supported so many creatures began to wither and die in the intense heat and drought. On land, life was struggling to survive, but the effects in the ocean were even more catastrophic. As the planet warmed, the oceans warmed too. Warmer water holds less dissolved oxygen. This meant that vast areas of the ocean became anoxic, meaning they had little to no oxygen. Marine animals essentially began to suffocate in the water. To make matters worse, the carbon dioxide in the atmosphere also dissolved into the seawater. This created carbonic acid, a process known as ocean acidification. The oceans became more acidic, like a weak, fizzy drink. This was disastrous for marine organisms that build shells or skeletons out of calcium carbonate, like the reef builders, the trilobites, and the ammonites. The acidic water made it difficult for them to form their protective shells. Their skeletons may have even started to dissolve. The oceans were becoming a warm, acidic, and breathless trap. There was almost nowhere left for life to hide. The evidence for this marine catastrophe is written in the rocks. Geologists can study layers of rock from all over the world that date back to this exact time. These rock layers tell a clear and terrifying story. If you look at a cliff face showing the transition from the Permian period to the Triassic period, you see a dramatic change. The older Permian layers are often dark grey or black limestone. They are full of fossils. You can see the remains of reefs, the shells of brachiopods, and the intricate shapes of countless other marine creatures. These rocks paint a picture of a vibrant, crowded ocean. Then you reach a specific boundary line in the rock. Above this line, in the layers from the earliest Triassic, the scene changes completely. The rock type is different, and the fossils almost completely disappear. The rich fossil-filled limestone gives way to pale, laminated mudstone. These layers are known as the boundary clays. They are almost empty of life. The bustling, diverse ecosystem of the Permian Sea is gone. It is as if someone simply turned off a switch. This sharp global change in the fossil record is the clearest sign of the mass extinction. It is a silent tombstone for a lost world. By studying the chemical composition of these rocks, scientists have pieced together what happened. They have found evidence of the low oxygen conditions. The dark color of some rocks comes from organic matter that did not decompose because there was no oxygen. They have also found chemical markers that point to ocean acidification. The lack of shelled fossils above the boundary line is powerful proof. Life that relied on building shells simply could not survive in the changed ocean chemistry. The reefs collapsed, the complex food webs unraveled, the oceans became a graveyard. The death toll was staggering. Scientists estimate that up to 96% of all marine species went extinct. It was the closest life has ever come to being completely wiped out in the oceans. Entire groups of animals that had dominated the seas for millions of years vanished forever. The complex ecosystems built by sponges and bryozoans were replaced by microbial mats, slimy layers of bacteria that could tolerate the harsh, low-oxygen conditions. For a long time after the main extinction pulse, the oceans were eerily quiet, a silent and empty world ruled by slime. The devastation was not confined to the oceans. Life on the supercontinent of Pangaea suffered just as terribly. The fossil record on land tells a similar story of sudden and catastrophic loss. The rich communities of synapsids, our own distant relatives, were decimated. The large, dominant predators, like the Gorgonopsians, disappeared. The big, slow-moving herbivores, like the tusked Lystrosaurus relatives, vanished in many places. The entire structure of the terrestrial ecosystem collapsed. The world of the late Permian, with its diverse and fascinating creatures, was erased from existence in a geological blink of an eye. The plants that formed the foundation of these ecosystems were also hit hard. The rapid climate change, the intense heat and acid rain from the volcanic gases caused forests across Pangaea to die off. Fossil pollen and spores preserved in rock layers show a dramatic shift. The diverse plant communities of the Permian are suddenly replaced by rocks that contain almost nothing but fungal spores. This fungal spike tells a grim story. It suggests a world covered in dead and rotting trees, a feast for fungi. It was a world of decay, where the forests had fallen silent. Overall, about 70% of all land vertebrate species went extinct. This includes reptiles, amphibians, and our own synapsid ancestors. The insect world also suffered its only known mass extinction. The sheer scale of the destruction is honestly hard to imagine. The world after the main extinction event would have been a desolate and empty place. The once lush landscapes were now barren wastelands. The survivors would have found themselves in a world stripped of its former richness, a disaster world where only the toughest or the luckiest could hope to endure. The survivors faced a harsh new reality. The planet was hot, the air was toxic, and food was scarce. The complex food webs that had supported a wide variety of animals were gone. For a long time, the ecosystems were incredibly simple. The few surviving animal species were often represented by huge numbers of individuals, because there was little competition. One of the most famous survivors was Lystrosaurus, a pig-sized herbivore. Fossils of this one animal make up the vast majority of all land vertebrate fossils in the earliest Triassic. It is a sign of a broken and impoverished world. Among the countless victims of the Great Dying, some losses were particularly poignant. The extinction of the Trilobites marks the end of one of the most successful and long-lived groups of animals in Earth's history. For more than 250 million years, these remarkable creatures had scuttled across the ocean floors. They were arthropods, distant relatives of modern insects, spiders, and crustaceans. They had survived multiple previous mass extinctions and had diversified into thousands of different species, adapting to countless marine environments from shallow lagoons to the deep sea. They were a cornerstone of Paleozoic life. Trilobites were true survivors. They first appeared in the Cambrian period during the Great Explosion of Life. They witnessed the rise of fish, the first plants moving onto land, and the evolution of amphibians. They came in all shapes and sizes. Some were tiny, no bigger than a fingernail. Others grew to be as large as a dinner plate. They had complex, compound eyes, some of the first sophisticated visual systems on the planet. Their hard, jointed exoskeletons meant they fossilized well, leaving behind a rich record of their long reign. They were, in many ways, the icons of the ancient seas. But the Permian Triassic extinction was a challenge they could not overcome. The very things that made the oceans unlivable for other shelled creatures also doomed the last of the Trilobites. The combination of warming waters, lack of oxygen, and ocean acidification was a death sentence. As the seas turned hostile, their populations dwindled. The final species of Trilobites, which had already been reduced in diversity, clung on in the last pockets of habitable ocean. But as the catastrophe unfolded, these last refuges disappeared. One by one, the final lineages flickered out. When the dust settled and the Triassic period began, the Trilobites were gone. After a reign that had lasted for 250 million years, their story was over. Their extinction represents the sheer finality of this event. It was not just a difficult time for life, it was an absolute reset. The Great Dying wiped the slate clean, removing not just species, but entire ancient groups of organisms. The disappearance of the Trilobites, along with many other groups like the sea scorpions and certain types of corals and brachiopods, marked the definitive end of the Paleozoic era. The age of ancient life was truly over. In the immediate aftermath of the extinction, the Earth was a strange and barren place. The vibrant, complex ecosystems of the Permian were gone, replaced by a ghost world. On land and in the sea, diversity was incredibly low. The planet was dominated by a few disaster taxa, hardy species that managed to survive the catastrophe and then spread across the globe in the absence of any competition. It was a world of pioneers and opportunists clinging to life in a hostile environment. The process of recovery would be slow and painful, taking millions of years. One of the most famous survivors on land was Lystrosaurus. This creature was a synapsid, a distant relative of mammals. It was about the size of a pig, with a barrel-shaped body, 2 tusks, and a beak for slicing through tough plant material. Before the extinction, it was a relatively uncommon animal, but afterwards it was everywhere. In some early Triassic fossil beds, Lystrosaurus fossils account for over 90% of all vertebrates found. Its success may have been due to its burrowing habits, which could have helped it survive the intense heat, or its simple, robust digestive system that could handle the tough, low-quality plants that grew after the forest died. In the oceans, life was also simple and sparse. The great reefs were dead, replaced by slimy mats of bacteria and algae. The few surviving marine animals included some species of bivalves like clams and gastropods like snails. These were generalists, able to tolerate the low oxygen and poor conditions of the early Triassic seas. For millions of years, the oceans lacked the complex food webs of the Permian. There were few large predators. It was a simplified, struggling ecosystem. Life had been knocked back down to its basics, and it had to begin the slow process of rebuilding. The recovery was not a smooth, straight line. The planet remained unstable for a long time. There is evidence of further warming spikes and environmental crises well into the Triassic period. Each of these events would have been a setback for life's recovery. It took an estimated 10 million years for ecosystems to return to the same level of complexity that they had before the extinction. This long, slow recovery highlights the incredible severity of the Great Dying. It was not just a storm that life had to weather, but a fundamental reshaping of the entire planet that left a deep and lasting scar. The Great Dying, for all its destruction, created an enormous opportunity. By wiping out most of the dominant species on Earth, it opened up ecological space for the survivors to expand into. The world of the Triassic period became a grand evolutionary experiment. The few surviving groups began to diversify, adapting to fill the empty roles left behind by the extinct Permian creatures. This period of recovery and innovation gave rise to the groups that would dominate the planet for the next 100 million years, and it set the stage for the evolution of our own mammalian ancestors. One group that thrived in this new world was the Archosaurs, the ruling reptiles. This group includes the ancestors of crocodiles, pterosaurs, those flying reptiles, and most famously the dinosaurs. Before the extinction, Archosaurs were a relatively minor group, but they were well suited to the hot, dry conditions of the early Triassic. They were mobile, efficient, and had adaptations for conserving water. In the empty world left by the extinction, they rapidly diversified. This led to the rise of the first dinosaurs in the mid-Triassic, creatures that would go on to rule the planet for over 150 million years. The Great Dying cleared the way for the age of dinosaurs. Meanwhile, our own lineage, the synapsids, had a very different fate. Before the extinction, synapsids like the Gorgonopsians were the top predators, but the Great Dying almost wiped them out completely. The few synapsid survivors, like Lystrosaurus, were successful for a time, but they were soon outcompeted by the rising Archosaurs. The surviving synapsids were forced into the shadows. They evolved to become smaller, nocturnal creatures. To survive in the dark, they developed better hearing, a keen sense of smell, and possibly warm-bloodedness and fur. These were the first true mammals. For the entire age of dinosaurs, our mammalian ancestors lived in the undergrowth, hiding from the ruling reptiles. They were small, shrew-like animals, hunting insects at night. It was a humble existence, but it was during this long period of suppression that many key mammalian traits evolved. The Great Dying had pushed our lineage to the brink of extinction, but the survivors adapted in ways that would ultimately ensure their success. When another mass extinction event later wiped out the dinosaurs, these small, adaptable mammals were perfectly positioned to take over the world. The Permian Triassic extinction event was the single greatest catastrophe in the history of complex life. It was a profound rupture in the story of evolution, a moment when the thread of life was nearly severed. The sheer scale of the loss is almost beyond our ability to grasp. 96% of marine species and 70% of land species vanished forever. It fundamentally and permanently altered the course of life on our planet. The world that emerged from the ashes of the Great Dying was a completely different place from the one that had existed before. The old order was gone, and a new one was just beginning. This event serves as a stark reminder of how interconnected the Earth's systems are. It shows how a geological event in one part of the world, the Siberian traps eruptions, can trigger a global cascade of environmental changes. The release of greenhouse gases led to rapid warming, which in turn caused ocean anoxia and acidification. It demonstrates the fragility of even the most stable and diverse ecosystems. Life is resilient, but it is not invincible. The Great Dying shows that there are tipping points, thresholds beyond which global systems can collapse with terrifying speed and completeness. The legacy of the Great Dying is written into the DNA of every complex animal alive today, including ourselves. The event acted as a powerful evolutionary filter. It determined which branches on the tree of life were pruned away and which were allowed to grow. The extinction of the dominant synapsids paved the way for the rise of the dinosaurs. The near extinction of our own ancestors forced them into a new way of life, shaping the evolution of the traits that define us as mammals. In a very real sense, we are all descendants of the survivors of this ultimate apocalypse. Today, as we face our own environmental challenges, the story of the Great Dying holds a powerful lesson. It is a cautionary tale written in stone. It teaches us about the profound impact that rapid changes in atmospheric carbon dioxide and global temperature can have on the biosphere. The world recovered from the Permian extinction, but it took millions of years of emptiness and struggle. The event is a solemn monument in Earth's history, a testament to the planet's capacity for both destruction and renewal, and a permanent shadow that reminds us of the delicate balance that sustains all life.